All right, folks. I'm looking forward to doing this work on section properties. So I've created a bit of a background document here. You can see it at this URL. And we are going to just sort of pop over to the section properties repo, and we can see sort of how this problem is currently described and how Robbie has set it up for. He's basically teed it up for me to fix. I just have to do the actual fix. So let's go on over to there, and I'll throw that back up there. We've got, let's see here, issue. This guy here, compound geometry, offset perimeter. So Robbie created this example, and we end up with this finite element mesh. Now, it may not be clear from the mesh what's happening right now, so I've created this little FAQ, this is what's at the link. This guy here. So I just give a bit of background here. So if you are tuning in here a little bit later, then just, you can get caught up by just reading this guy here. So today's agenda here is this. We got two rectangles like this. We put them side by side, and then we do the offset perimeter method on this compound section. So I put two rectangles together and I combine them together with the plus operator to create a compound geometry. So now this is my compound geometry. And then if we wanted to dilate it, doing the offset perimeter here, basically adding material onto it, growing it out sort of by a radius, we could say a radius of 50 units. And then what happens though is we get this crappy sort of overlap region here. And what we want is this sort of these overlap rectangles to sort of not exist. We want this to sort of basically have a straight line going up and down. In other words, we want it to look like this. So that's what we're working on today. Now, when Robbie brought this up here, I spent a bit of time thinking on it and doing some notebooks to sort of try some things out to see if I could kind of come up with like a quick sort of geometrical sort of series of operations, set operations to fix it, but I could not. And so I just left this like this on June 10th, being like, I'm not sure how to fix this one yet. So I've been thinking about it since then, and I now have an idea of how to do it. And I did sort of a quickie test, and I think it works, but I don't know if it works. It'll pass this test, but I don't know if it passes sort of like all tests. I don't know if it's robust. Let's work on the solution first, and let's try and put it together. First off, let's start with this. This is the test that Robbie created, and he actually created a pull request here, and he's left it open. And in this pull request, there is a branch. There's this pull request basically is a branch that is from a branch that has a test in, a unit test in that currently fails. And that's this guy here, 332. Like this. So we've got this test compound rectangular offset now in this pull request. And you can see here the test fail. So once I do a commit here, that fixes and allows the test to pass, then all these checks will pass, and then we'll be able to merge the pull request in to the original job. You can see this is open on October 9th, 2023. Have not been able to get to it till now. So I'm excited. Let's get into this. And let's use GitHub Desktop here. Let's see if we can get, let's see, we want to open up, let's see, pull requests. We want to get this pull request here as our branch. There we go. So now I should be able to go into VS Code, see this test. What was it called? Test compound rectangular offset. Let's pull that up. Tests. Let's see. Test geometry is probably under there. Let's take a look. Where did he put it? Oh, looks like I'll just have to look for it. Do we have a commit? Here we go. Where's the test? Test compound. Test offset. There we go. Let's do that. Test offset. Here we go. Boom. And test rectangular offset. Here we go. Test box offset. Test compound rectangular offset. Here we go. All right. So corrode. So the corrode, I don't know if the corrode works either, but it looks like test compound rectangular offset is the one we need to worry about. So we'll do that first and then see how it goes. So there's the test here. So I need to change the code in the geometry and compound geometry methods here. So the operation we're performing here, let's go back. The operation we're performing is this one, offset perimeter, a method on compound geometry. Now this only affects compound geometry because for a regular geometry, it's just one shape. We can dilate it and erode it, and it doesn't have any fuss to it. It just works. Because it just works in shapely. But with the compound, though, this behavior is sort of intuitively what we'd expect, but it's not clear to the geometry that that's what we want. So, because what we're doing is we are dilating each geometry separately, and so we're basically kind of want them to like act like a bubble, right? So they like press up against each other and then grow along a straight line. But that behavior is complicated. So let's put the example that he's got in here. Where is let's go back to the issues. Let's start with that. We'll copy and paste that into a Jupyter notebook. Now I've already pre-set up. I've got my section properties environment. I've already installed section properties in a new conda environment. I've set up a new Python, IPython kernel into that environment. So I can just like select section properties here for my list of kernels. And now I'm running code in my conda environment, my virtual environment. Sorry, it's not a virtual environment, but I'm just going to say that word. My environment for working on section properties. So the only thing in this environment is the section properties repo and all of its dependencies for working on it. So that's what I'm running my code from. And I did an editable install. So now when I run this code and I make changes to the code in VS Code, and I go back to run it, it will reflect those changes as long as I do an auto reload here. So let's load up auto reload extension. Auto reload, and I'm going to do auto reload option 2 for re-import on every run. And let's run that as the first cell in this notebook here. There we go. There we are. All right, so here we go. I'm going to plot this mesh. Module not found error. What's the problem? Blah, blah, blah. No module named triangle. I know what I did. I installed it from the main branch and not from this old branch. So what this branch should have done is, because this is from like October, right? I should merge into it. Choose a branch to merge into. Let's merge main master into it. And it's going to pull it up to date here. Let's see if there's any problems. Looks like we're all good. And so now let's try this again. Restart the kernel. There we go. Because the changes that were made to section properties is that we went away from using the triangle library to using the sci-triangle library created by Marianne Wachter, and it's a nice change now because we can now be super current with section properties. It will work on the newest Python, the newest chipsets, because sci-triangle is set up to automatically publish and release on these new versions. So it's going to make a big difference here to section properties and anyone else that uses the triangle library. Okay, so here's what we got. Now let's try. I'm going to take this mesh creation out. We don't really need this because in order to sort of see what's happening here, we just need to look at the geometry itself and we'll see what's going on. See, there it is. We got this goofy business here, these little circles. So here is what I'm thinking about for how to fix this. Let's go back into this so we can sort of see bigger versions. So we want these to sort of expand outward and treat this line here as the line that they're joined on as like something that does not change, right? So here's the idea. Let's find the lines between the two or more geometries, the lines between all the geometries where they share an edge, right? Let's find where those edges are, and then let's take those edges out of the equation, right? So if I've got two boxes here, two rectangles, and I take an edge out, what am I left with? I'm left with two line strings. So it'll be a line string that looks like a C shape on the left and a line string that looks like a reverse C shape on the right. And so now I've got those two line strings there. Now I can buffer expand out or dilate those two line strings, right? And if I dilate it, say, by a radius of 50, it's the same as whether I dilate the polygon by a radius of 50. And so I can create a buffer on that line string, yeah? And then I can take each of those buffered line strings and union them, join them back to the original geometry, because of course the source line is it's still the shared edge. So now when I union them, I just get that buffered shape, but only for those three edges, yeah? And so then when we do the same on the other side, then we can sort of union them both those two pieces together, and then we end up with this shape here. And so this is actually created through my tests that I did, and we're going to go ahead and recreate that. I actually don't have them written in front of me here. I like wrote them once, and I was like, I'll delete them and write them live. And so I'm going to be going from, not really from memory, but I remember that I came up with the process. So let's go through that. So the big idea here is to break each of these geometries out of the compound geometry. Okay, so the approach I'm going to take is I'm going to write it in JupyterLab first, and like as a script, and just figure out the process. And once I've got the process working, then I'm going to put it into VS Code. All right, so that was a nice sort of 10-minute intro here. Let's get writing some code here. So the big idea is compound geometry. The compound geometry is stored in geoms. Let's make the name of this, instead of geom, let's change it to compound geom, like that. And so we know what we're working with all the time. Okay, oops, what do I do here? I've got geom and, okay, I got to update this one as well. There we go. Okay, compound geom. Now in compound geom, I can get the underlying section property geometries from them by doing .geoms attribute. So I get a list now of section property geometries, and so I can index them in like this. So there's the left one, and here's the right one. Okay. Now I don't want to have this dilated one. I want it before that. I want it just the two rectangles, like that. So geom 0 and geoms 1 are my two. Now from there, I want to sort of take out the joined line, right? So the way I thought about doing this originally was like, okay, I will convert from each of these, I will get the underlying shapely geometry, which is under the .geom attribute. There's the shapely geometry, and then this is now a shapely polygon. We can see that by doing type. So that's our underlying shapely polygon. Okay. So here's the thing. I want to iterate through every geometry in a compound geometry, and for each of those geometries, I want to test. I'm going to say, okay, loop through them all, and then I want to loop them all again, do a double loop, because I want to compare pairwise every geometry to every other geometry, and make sure that they're find all the possible shared edges between them. So they've got to do a double loop. So the idea here is, now I'm going to do a double loop. I'll get the polygon. So I got a polygon here, and now I want to get the exterior, because a shapely geometry is divided into an, shapely polygon is divided into an exterior and an interior region. The exterior is the linear ring. I can convert that linear ring into a line string. So in order to do that, I need to import the line string from shapely. We'll do import shapely. Oops, let's do from, no, I'll do import shapely as shape, because there's going to be a bunch of sort of various things that I want to get in there. Import shapely as shape. So now I can do shape dot line string, and this will convert the linear ring, which is a closed line, into an open line. Like, it looks the exact same, but the difference is that this isn't closed. It has no area. Area is 0. Now, I don't know where it's closed. It might be at any one of these vertices. Like, it might be a line that goes like this, 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 or it might be a line that goes like starts from here and goes around this way. So if I take out one of these lines, then I might end up with like a multi-line string, like this is a line string here, and then this is a line string. I'll deal with that later. So this is the idea. Turn it into a line string, and then I want to find out where it has edges in common. So my original thought with this is like, okay, I've got a line string. I want to break it out into individual segments and then like test individual segments against all the other individual segments. So in other words, a quadruple loop. 2 loops to do geometry versus geometry, but then I got to bust each one out and do line string versus line string. And So I was spending a bit of time thinking about like finding how do I bust that out into from like a polyline into individual segments. And I was reading the Shapely documentation, and I found that there is a function called shared paths. I don't need to bust this out into a quadruple loop. That's kind of nuts. I only need to use shared paths, and it returns the shared paths between geometry 1 and geometry 2. So, you know, in fact, I don't even know if I need to do a line string even. Maybe I just need to do, do I need to do exterior? I don't even think I do. I bet you I could just do shared paths, Shapely.shared paths between geometry 1 and geometry 2. And geometry 2 is in, there we go, geoms 1. What do I got here? Problem. Geometry is not lineal, right? I do need the exterior. I do need to have it as a linear ring, at least it sounds like. There we go. Okay, perfect. So, shared paths between these two linear rings gives me this line. Excellent. That's the key thing that I want. Now, if I take that as my shared path, I'll call it the shared path. Brilliant. Brilliant naming here. Okay, and now let's break this out. I don't want to have to type this junk all the time. Here, like that. So let's call that geom A, and then this one will be geom B. There we go. And then I can just replace this with geom A and this guy with geom B, because I'm going to be referencing this for probably a few times. All right, so there's my shared path. Now, I want to do geom A is my linear ring minus the shared path. Do a set operation here. Boom, that's the shape that I want. Now, what is this? Is it a line string, or is it a multi-line string with multiple kind of pieces? Multi-line string with multiple pieces. Same, what about geom B? Oh, that's like a full line string, right? So I don't have any control over how that operation results. But what I do know is I want this to be one single polyline, right? If I have it as separate pieces, then the results don't turn out quite like I expect. So let's keep going on this. Okay, so that's the thing. I've got the shared path, and then I'm going to do, for each geometry, I'm going to do this sort of subtraction operation. So let's go through. And I'm not putting this in a for loop. I'm only working with two geometries, so I'm just going to work it out all step by step. So geom, so I'm going to call it source. This is my buffer source. A is going to be geom A minus the shared path, and then source B is going to be geom B minus the shared path. And then let's see what source A, yeah, and source B, just like we expect. Good, okay. Now I can buffer source A and source B. Dot buffer, and then I give it, say, 50. Whoa, maybe too big. What is my scale here? I have no idea. Oh, I'm already at 50. Let's make this 500. And let's see. Oops. I clicked it, but I didn't actually type a value. There we go, 500. I'll do Control R to run all. There we go. Okay. So there is my sort of buffered path here. Now in buffer, so this is the line here. It starts here where my mouse is, and it goes to this, it's like a center line here, right? And it's buffering out on the end. I don't want it to buffer on the end. Because if I do let's put these both into a geometry collection. We can see this. Oh, I gotta do shape.geometry collection. There we go. Put it into a list. There we go. And then geom A, or no, source A. Oops. Wrong bracket. There we go. So you can see that like this is the center line here, and this buffered out beyond the end here. There is a way to control that behavior, and that's with a cap style. Well, and that's this guy here. By default, it's round, as in it gives you a rounded cap at the end of it. But you can also do square or flat. So we'll say, if we do square, we get it like that. And then if we do flat, it stops right on the end of the line. We want it to have that shared line, right? So we want that line to continue basically right from here, right? Now look at this. It buffered nicely here, but not here. And that's because this is one line string and this is another line string. And this whole thing, the source A is a multi-line string. So that's why when we did flat cap style, that means that it's going to do a flat cap because this is the end of this line and this is the end of this line. So how do we fix this? We want all of this to be a single line. So now in Shapely, I believe there's another function here called line merge. I thought it was merge lines, line merge. So let's put line merge in this whole thing, and let's see if that fixes it. Hey, that's where we're doing it. Okay, so now we need to do shape line merge on anything that we do as a source here. We want to make sure we do line merge on it because we don't know if it's going to be broken up into multiple pieces or not. This is a way to make sure that it's contiguous. How do we know it's going to be contiguous? Because we're taking it from a polygon. So the polygon exists, therefore we take one or more. Ooh, we could take one or more lines out. What if we take two lines out? What if there was a shared here and here? Oh, let's worry about that later. Okay, let's think about this. All right, so we'll do another test afterwards and see if we can adjust this to make it more a robust algorithm. But right now we're just getting a test proof of concept. Okay, so there's our two sources. So that's buffer. I'm going to do buffed A and buff B is I'll buffer by some parameter here so I don't have to type it. Offset. There we go. So buff A will be source A dot buffer and give it the offset and cap style flat. Let's do that. We don't, yeah, whatever. There's only two of them. I'm not going to parameterize this, I don't think. Of course I'm going to do it because I'm going to do more tests afterwards. Cap style. There we go. This is cap style. And that's going to be that guy. So let's take a look at buff A. Perfect. All right, now we'll do the same with buff B. And source B. Okay. Now, we've got buff A and buff B, and we want to now merge them back, or do a union with geom A. So buff A, and then we do union geom A, and that's geom A is the exterior, the line there. So maybe I don't want to do the exterior line. Let's change this. So that way, like that, and then I'll just do the shared path as dot exterior down here. There we go, run that. Ooh, not quite what I was looking for. All right, so let's see, what did I goof up? So geom A is this guy. Let's do a geometry collection of the two of them so we can see them both together in the same space. So buff A and geom A. Something I missed. Shape.geometry collection. Shared path, source A. Oh, I see what I did here. Okay, I got to do dot exterior again. There we go. There we go. That's what I want to see. Okay, yes. So here's my geom A, the original geometry, and then this is it buffered, and you can see how this line is preserved now, yeah? So that's what we want. Now, let's do, I'll call it new A equals geom A union buff A. And new B is going to be geom B union buff B. And now I can do new, put these into a geometry collection, dot geometry collection, and that's new A and new B. Hey, that's it. So this is the sort of the general process we want to follow here. Not a whole lot of code, which is nice. So, but there's one other problem here, which is this is only for two compound objects with one shared line. I would call this the special case. What if we have three stacked together? Let's say we had like 1, 2, 3. What happens then? So first off, let's take this and just put it into like, some sort of algorithm, parameterize this a little bit. Or you know what, screw it. Let's write a function. Let's do it like that. So let's go here. And let's first start off by merging these cells. And I'll do that by doing Shift and down arrow. And I'll do Shift M to merge the cells together. Let's put this into a function. Def better offset. And we're going to take a list of geoms. Let's start off just with shapely geometries right now. Say polygons. Polygons is going to be a list of shapely.polygon, and then it will return to us a geometry collection. Let's have it turn a list of polygons again. Shape.polygon. There we are. And I'll put my little doc string here is test function for improved compound dilation. I'll change that obviously once we get it done, but this is where we're going to start. So instead of geom A and geom B, I gotta do my for loop, right? So I've got for poly A in polys, and then I do another one for poly B in polys. So I'm gonna loop through them all, and that way I can compare them together. So I want to say if not poly A equals poly B. So if I don't want to do this operation if they're the same one, right? So then, or let's just make this a continue clause. If poly A equals poly B, continue. Then we can avoid maybe having a bunch of indents here. Here we go. And or let's just, that's weird. So let's do it like that. Okay. So that means like, if they're the same, then just skip this iteration on the loop and go to the next one. So all right, so now we've got this guy. So we want to get our test geometry. So we've already got poly A and poly B here. That's what we've got. Now we want the shared paths. So shared path equals shape.sharedPaths. That, and that's not geom A, it's poly A and poly B. Poly A, poly B. Great. And now we're going to offset is going to be a parameter equals is going to be a float or whatever, some number, and cap style is going to be what we need though. We're not going to parameterize that. That'll just be hard coded. And so then we're going to convert these into a source, source A and source B. Let's just take this whole thing now, paste that in there. Shift tab it to the right indent, and now that's poly A and poly B. A exterior minus the shared path, line merge on them both. Then we're going to do the buffer. And source A, source B is going to be the offset amount with the cap style, and the cap style is flat. Might as well. Already got it written there like that. Let's do it like this. Okay. That seems a little bit. I think that gives it more importance than it needs to have. So let's just take this out and just do flat. They're right beside each other, but it's not like we're going to miss one or the other. And then we've got the new, which is new A equals this business here. So let's just do this exact same thing. There we go. And now, what are we going to do with these? Now that we've got new A and new B, I think we're going to accumulate them. And where are we going to accumulate them? I don't want to have this, because we're running, I don't want to have to do this on A and B, and then also B and A. So, maybe what I want to do is instead do combinations. I want all combinations. Exhausted, yeah. So take one, yeah. So instead of doing a double loop here, I think it would be better to do itertools. Do we have itertools already in here? We do. Awesome. Great. So import itertools, and then we've got itertools dot combinations. There we go. So I give it an iterable, and I give it a number of combinations. It will give me all possible combinations here. So I can go through the list of combinations, the list of indexes. So that's what I'll do there. Okay, so here is let's go through, let's create combinations. Then I don't need to worry about this poly A, poly B business. Okay, so let's do poly combos is itertools dot combinations of polys and the polys, and I want length 2. Right. And now I do a single loop. Take this out to a single indent level. For poly A, poly B, because it's a tuple, and I just unpack them in poly combos. Now I've got this. And now I just have a single accumulator. And now I'm going to have, let's get rid of all this junk here. This is starting to confuse me. Actually, let's just comment it out. Maybe I want it later. All right, so now I'm going to do new A and new B both into the accumulator. Act.append new A and new B. There we go. And then I'm going to return my accumulator. Simple. It's in a way you could think of this as a transform recipe. Turn act. All right. So let's test it out here. So better offset. The nice thing is now that I can run any number of polygons through this function, I can just see what comes out. So let's try it with our just regular list of polys here, which is rect1 and rect2. Now I'm not going to put in a compound geometry. I'll just give it rect1 and rect2, but I need to get each constituent shapely geometry from rect1 and rect2, and I'll put those into a list. Keep it simple right now. Rect1 dot geom and rect2 dot geom, which gives me the underlying shapely geometry. What is it not to, oh, rect no underscore. Offset, right, 50. Okay, it gives me a list of polygons. I can put those into a geometry collection. And I don't need to put it into a list, it's already in a list. Shape.geometry collection. There we go. Okay, cool. Right, so let's now create rectangle 3. And rectangle 3 will be a rectangular section. Oops, get back onto the screen there. It'll be a rectangular section. And just the exact same here. You know, I don't need to type this again. I just do a rectangular section. I just do rect1. Rect1 knows already exists. So when I do an align operation, it doesn't move the existing one. It creates a copy. So, and that's by design. So we can allow it to do this sort of thing. Align to, and we want to align it to rect2 on the right-hand side. So that'll give me 3 rectangles now. And I can see those by putting them all into this compound. Rect3. Oops, I did it again. All right. And there I've got my 3 rectangles here. Okay, so I got rect3 now. Let's try it out with rect3. Does it break? What do you think? Rect3.geom. Hey, it breaks. Oh, and it breaks fun. Ah, that's good. That's really good. Okay. So, what is the issue here? I think it's because our assumptions. So, you know what? Maybe I've got to, let's go through each one of these and look at the pattern it gives us here. Damn, that's cool. Let's go through, let's just sort of display stuff as it's happening. Let's look at source A and source B as they fly by. We'll do display, source A. It displays like print for Jupyter, and it allows us to show the rich formatting instead of just like the text a representation of source A and source B. So let's go through there and see what happens as we do this. Look at this, hey. Source A, source B, that looks like we want. And then source A and source B, because they have no lines in common because they're the 2 end ones, right? and then source B and source A. So, okay, let's add some logic in here. What is going on? So we are not checking if there is a shared path or what the shared path is. Let's look at the shared path display. I bet you there's an empty geometry here. Where is the shared path showing? Okay, shared path, yeah? Source A, source B. Shared path empty. Source A, source B. All right, let's check this out. So shared path is going to give you an empty geometry, right? So let's say let's put all this business, let's say if shared path dot, I think this is going to be is empty, I think it's like that, then continue. Let's try that. Let's see if I got the name of the function, the thing right, is path. Oh, it didn't do anything. It still gives us the it's not the exact same result. It's a little bit different. So maybe that's not the key. So let's just take that out again. And here, I don't need to keep this junk here. This is all disposable now. Okay. So let's see. Yeah, okay, so I've got multiple layers of overlaps here. If I don't do this, you can see that because it's a darker color here, like its transparency is overlaying on each other. So the more layers, the darker it gets, the more opaque it gets. And so the shared path here, if shared path is empty, then continue. And then that's just generally what we want to have happen. So we can see it's gotten lighter now, but look at this funny shape it's creating. And where is that coming from? So what is it merging? So let's see, buff A, and let's put buff A and maybe somebody saw this, but maybe if you didn't, it's not in the chat anyway. So let's do this. Do you see what I did? I've got geom A, not poly A. That was my old, here, you know what they say in Jupyter, right? Restart and run all. Let's do that. Restart and run all, or it didn't happen. Let's get rid of this out of here. Oh, no, don't do that. I don't need that. Iter tools, keep that import. There. Restart and run all. Oh, where's my shapely import? Did I delete that as well? Let's put all those in there. Import shapely as shape. Restart and run all. Okay, so this is less crazy and is starting to look closer, but I think that the problem is we have this guy in the middle. I think there's just one extra geometry being created here. That's not right. That's what it appears to be. Let's just go see them all as we go through here. Let's iterate through. What do we want to see? So geometry, we want to display, not display source A, source B. Let's take that out. Put this down here maybe. And let's do geometry collection of source A and buff A. Geometry collection, shape.geometry collection. And do that. Oops, what did I miss? Oh, I see. Source A. And gotta give it a... Oops. I missed a couple things. Okay. First, gotta call it like that. Then you gotta put more stuff in it. Buff A and buff B. And then we gotta close off these parentheses. There. Yeah, okay. So this is looking correct, but we got something going on in the middle here. We need to have the middle line string. We need to have this line here in the middle on the top box. We need to have that one also buffer. But how do we do that? In order to do that, Because right now, these are the only n units. So why am I seeing this one in the middle? What's happening with that one in the middle? Source A. So I'm surprised that I'm seeing new A and new B. I'm surprised that I'm seeing this one in the middle. I would expect this one not to buffer, and just to be like the original. Seems like this is the right shape on the end. That's the right shape on the end. What about this thing? How is that happening? I'm not really clear yet on how that's happening. So let's display new A and new B. Actually, let's just look at what's in the ACK. What's in the ACK here when it comes out? So there's that guy. Let's copy that out. Result. And let's just print the result here. Is that useful? You got 1 polygon, 2 polygons, 3 polygons, 4 polygons. That's one more than I was expecting. So where's that 4 polygons coming from? So we've got all these combos here. And so I'm seeing source A and buff B. And yeah, that's exactly right. So where is this 4th polygon coming from? What's being added to the accumulator? New A and new B. So that's new A and that's new B. Oh, look at that. That's 4 polygons there, it looks like. Wait, let's take a look. But I'm just shrinking them down. Buff A and buff B is going to new A and new B. Yeah. So poly A, poly B. So yeah, there's 4. I'm iterating through this. How many times? Let's index it. So I'm iterating it through. No, I don't need to index it. 1, 2. There's 2 iterations. I get 4 geometries, so that makes sense. Getting 4 geometries here. And so new A. Let's just look at new A and new B as they come out. Take this out. New A and new B. If it's obvious to somebody here what's going on, then you tell me, because I'm not seeing it yet. New A, new B, new A, new B. And let's look at the coordinates here of new A and new B. 500, 500, 1,000, 500. Let's geometry collection them all together, which is what we did here. What's going on? 1, 2, 3, 4. 1, 2, 3, 4. I see what it is. It's this one and this one and this one and this one. I see. And then it just happens to create an overlap region in the middle. That's not actually part of the original shape. I see. Okay, so I need to do another test here to see if new A is equal to, is in the ACK. If any of these are in the accumulator already. Okay. If new A not in ACK, ACK.append, new A. LF, new B. Let's do LF. Let's just do if, because that condition can be true, and then this condition can also be true separately. Not in ACK, then ACK.append new B. There we go. Let's try that. Did that change things? It doesn't seem like it changed anything. Because new B and new A, ACK. So what do we have here? We got 1, 2. They're not the same. 3, 4. Yeah, they're not the same at all. So what do I want? What do I want to have happen here? I want to have this one and this one, but not its complementary one here. Damn, it's getting complicated. All right, so this joining with this middle one. And the middle one's, here's what I'm worried about. And this was a problem, or this was a solution that I needed for another problem in section properties. And it is, I might need to build a network, like a graph of which geometries are connected to which other geometries. And because that allows me to know if it's got if it's a geometry that has 2 connections, then I want to calculate the shared path of both connections at the same time. and give me 2 straight lines. Yeah, I do need to build a network. Because how else would I know what's connected to what? All right, so let's go into section properties. I have solved this before. And so where is that going to come into it? Yep, it's going to have to be a network. All right, geometry. Where did I do this? This is in tests, not in tests. We want source. Pre-geometry. And did I walk? Yeah, I did. Here we go. Check geometry disjoint. Okay. Now, is this a function that I can reuse? Because damn, that'd be convenient if I did that. All right, so I did this thing where I defined a function in another function here because the only place I was going to need this function is in the context of this other function. So it returns true if any polygons in the list of polygons are disjoint, as in they're not connected to anything. Okay, so that's useful, but you know, dang, I think walk network needs to exist on its own. Because what do I get here? I get a node and network, nodes visited. All right, so it's going to walk the network using recursion, and it's going to give me the nodes visited, right? And then if there's, right, so this is a special application of walking the network. So I need to, all right, let's figure this out as we go. Blah, blah, blah. Okay, so the network is going to be a dictionary of integers and a set of integers. That's what I want. Okay, so this will tell me the index of a polygon, and it will give me a list of integers for the network. Okay, so that's good. Okay, so intersection, poly A, poly connectivity, add. Yeah, so I'm doing a double loop. If they're not the same, do this. Okay, and then walk the network. You know what? I don't even know if I need to walk the network. I think I just need the network. Let's just take this. We're just going to take this right now and run it through my list of polys here. So this builds the network here. Let's call it geometry network. Build geometry network. And it's going to take a list of polys. Lop, list of polygons, shapely.polygon. There, and it's going to return this dictionary thing here. I'll just say dict. Here. Now that gives me this. Indent that, and I return the network. Okay, so now I'm going to do, so I'm going to call this my test geoms. There we go. And then I'm going to build geometry network. Let's split this cell up. Build geometry network and test geoms. Let's look at it. Okay. All right. This is good. So this tells me how many connections it has, and then I can change my behavior based on that. Okay, this is nice. This is better than the combinations here because it says I iterate through each one, and it tells me which one it's connected to. In other words, it gives me the combination. Now, does it also duplicate? No, it doesn't duplicate. It doesn't seem to anyway. It doesn't say, oh, it does, yeah, because this is 0 is connected to 1, and 1 is connected to 0 and 2. But I don't think that's the problem here. I think this is exactly what we want. So, all right, let's go with this. Let's build let's get this function out here as build geometry network, and then we're going to go through here, instead of doing poly combos, we're going to say geometry network. Geom network equals build geometry network. Yes, God, it's amazing how often a network is a solution. All right, so polys, there we are. Build the geometry network. Now we need to iterate through the keys, which will give us, if we're going to iterate through every polygon, which is convenient. And so that's going to give us the poly index and the connectivity. I'll call it connectivity set. I'm not going to call it set. That's silly. Connectivity, polyindex connectivity in geom network dot items. Okay. So now, shared path is going to be the shared. We're going to check the shared path between the original. So we'll call it the poly, or a poly orig, or poly focus. I don't know, poly orig, let's say. Equals, and so this is the index. So I need to index into the list of polys to get it. So that's going to be polys, poly index. And now the, I don't want to deal with this as a set. I can just convert this to a list. So I'll say connections, or connected polys equals list connectivity. So, because I can't remember for set. Do I have to do anything to iterate over it? A set? I'll find out. Let's see. All right, connected polys, list of connectivity. Great. So I want to get all of the. I want to convert a connected polys into. That's not connected polys. That's connected indexes. And I want to get the connected polys. So I'm going to create a list comprehension. Let's go do it like this. Connected polys. All right, we're getting close to the hour here. Let's see if we can wrap this up. Connected polys. Bam. And we're going to say poly. We're going to do poly. Get the polys index. That will give us the actual polygon for index in connectivity. There we go. And then we're going to say the shared paths between, oh no, shared paths only takes 2 arguments, does it? Oh, it only does 2. How awesome would it be if I could give it an array, geometry or array-like? What if both geometries should be line strings or arrays of line strings? Okay. Maybe this works. All right. Okay, so let's do that. So connected polys is a list. Does that count as an array, or does it need to be a NumPy array? Let's find out. So poly orig and connected polys. There we go. If shared path is empty, so the shared path, so we want what comes out of the shared path. What if we can't line merge? This is assuming connected. Okay, so let's just stick with this. Let's look at some shared paths here. Let's just return shared path, which I should probably use as a plural now because it could be paths like that. And then let's just comment that out just to not confuse ourselves. And let's just return that. Oops, what I goof. Oh, I left that uncommented. There we are. And I'm returning shared paths. Let's comment this out as well. All right. So now, better offset. Better offset. Test geoms. Oh, sure. Yeah, the 50, whatever. Geometry is not right. I forgot the polys. We don't want that. We want polys dot exterior. Shared path is not defined. Okay, so we're already in a good spot here. The path that ran. Let's just do that. Okay, so geometry collection, multi-line string empty, multi-line string. All right, so that's just the first one. Okay, let's accumulate them. Act.append shared paths, and then return the accumulator. All right. Multi-line string empty, multi-line string geometry. So so second geometry collection of a multi-line string. Okay, so we got 2. All right. Okay, so this is what I want to get. So what I think is, 50, 500, 500, 500, 0. That's a vertical line. Yeah, same X. Yeah, vertical line. So those are the two the left and right edges. So that when I do the difference there, then I will get the top and bottom lines, which are the ones I want to buffer. Good. So this is the right track. So let's see. We're just going to wrap this up quickly here. All right. Now, so this is what I get from the shared paths is I get a geometry collection, and I can get some like empty stuff, and then a multi-line string, which means I got to like go into the I got to like index into it or some crap or iterate through it. Let's go. Okay, so I got multiple layers of iteration here. Can I like avoid some of this junk? Geometry collection. I'm getting a geometry collection for every one of these iterations. This looks like a helper function called extract shared paths. And it's going to get a list of, or an array of geometry collections. Array of geom collections. And that's going to be some array. I'm not going to worry about the type right now. And I'm going to return, what do I want it to return? I want to give me basically a list of line string. Is it going to be a list of multi-line string? I want it to be just a list of line string. I think I can get that. I think I can do that. Line shape.line string. Okay. So for geometry, all right, so each one of these is going to give me an array. Okay, so I get the one array, and it's going to have so I don't know if there's more than one geometry collection into it. Okay, so I got to go loop through. For geom collection in array of geom collection, for line string, or for multi-line string in geom collection dot geoms, it's to access the underlying geometries of the collection. And then I want to do a merge lines. I'll say line string equals shapely dot merge. Is it line merge? Dot line merge on multi-line string. And then I want to accumulate those. So I'm going to put my accumulator down here. For geometry collection, I could have multiple geometry collections. No, I need to put my accumulator up here. Acc equals that. And then I'm going to do lines, acc dot append line string. Return acc. Let's run that. Is on this better offset. So what's an input here is one of these better offset items here. So extract shared paths better offset. Let's just copy and paste that, jam it in there. And shared paths, and it's going to, I want just one of them. Let's see what we get. Okay, you got to check for the geometry collection being empty. If not, if geom collection dot is empty, continue. If geometry collection dot is empty, continue. Why? Oh, it comes with a subgeometry. Oh, line string is. I got it wrong. If MLS dot is empty, continue. There we go. There. So that looks like it's working now. Okay, good. So let's try it now with second one. Hey, that's what I want. Okay, so there we go. We got extract shared paths up and running. Let's put that up with our other helper function, our network. Okay. Okay, so extract shared paths. I'll call this gobbledygook, mucky shared paths. Shared paths equals extract shared paths, mucky shared paths. There we go. And now I've got now I've got the shared paths here, and that comes out as a list of line string. Maybe I want that to be a geometry collection. That's fine. I won't change my helper function right now. Or maybe I want a multi-line string. Let's make it a multi-line string, because then I can do the subtraction operation, which is what this is all about here. Here. Okay, so now I've got source. And I might have multiple sources here, and that's fine, I think. I'll just call it source. Because I think I only have one source now. And shared paths is poly-orig dot exterior minus shared paths. And that's going to be a multi-line string. Let's call it. So let's put that as like multi-line string here. All right, we're at the top of the hour, but I think I can get this done. Shapely.multi-line string. Shape.multi-line string. Bang. Done. Okay. Source. Buff. Buff equals source dot buffer offset cap style equals flat. And then I'm going to new equals poly-orig union buff, and then ack.append new. All right, I think that'll get us there. Let's try this. Where's our test? Better. Here, let's do it here. Better offset test geoms 50. Oh, it's already a linear ring. What's going on? Source, line merge, poly-orig.exterior. Linear ring object has no, did I already make it exterior? I did. Oh, my bad. Done. And, hey. I got a list of geometry collections. Let's put this into a geometry collection. Shape. All right. I am not unhappy about this. This is great. This is not exactly right, but it's just like a minor thing that we need to fix. But damn, look at that. That is the ticket. So what's the problem here that I'm missing here? A poly-orig, that's why. Let's rename this. Poly-orig exterior. Let's do it like this. Poly-orig. Poly-orig equals poly's poly-index. There we go. Poly's orig.exterior. Orig. And then I just got to update this. Poly-orig exterior, 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 and then oh, not this one. Source, yeah, okay. Here we are. Let's try it again. Hey, bam! All right, now is this proof that this is a robust algorithm? It's not proof, it's just evidence. Evidence to support that it looks like it could be a robust algorithm, but I have a feeling it is because we're walking in this network. It has knowledge of what's connected to what, and it will do these operations as whole arrays over the whole thing. So I'm gonna call this good, and I'm gonna put this because this is definitely gonna solve the current test function. But you know what? I should include this other. I should improve the test function to be 3. Because that is a better test than just 2. All right. So here we go. That is what we're going to put into the code base. But I'm going to I'm going to build this geometry network. I'm going to refactor, build this geometry network. I'm going to take this out here. So I'm going to make this build geometry network instead of making this is disjoint. So that way I can do. Oh, what do I do here? Yeah. So I'm going to build geometry network. That's what this does. Builds the network. Pass it in here. Yeah, so I'm taking this out. I already wrote it, so I'm not going to... I'll take it from my Jupyter. Build geometry network. Boom. And let's put that above. Let's put it below. Because it's going to be a dependency. There we go. build geometry network, and just look at a polygon, and then we got, what else? Extract shared paths, copy, paste. That's also one of the ones we're going to need. I'm going to put better doc strings on these, but these are internal functions. They're not intended to be used outside of the library. They're just meant to be used internally. Oh, I got to, from Shapely, import line merge or something. From Shapely, import line merge. There we go. Oh, where's my box? There we go. Okay. So there's that. I got to do my types on this guy. Right, and then this guy, better offset, is going to be the implementation, I believe, for compound. So I'm just going to put it in as a class compound, and then def offset. There we go. So this is currently the implementation. I'm going to put mine in as comment above. And then, you know what I think? Now, here's the interesting thing, is that dilation and erosion are two separate conditions. And I take care of that here. So I'm going to just copy and paste this, not here. I'm going to leave the eroding condition because I'm pretty sure that works beautifully. I'm pretty sure. And I'm going to change this for the dilation condition, the ballooning condition I called it. Let's take that out. And it's got some code in there that I'm going to need because my code only works with Shapely geometries and it needs to work with section properties geometries. So where's my indent? Here, like that. Okay. So I need to go ahead and do some fuss to put this all together here. But that is going to be the new implementation for this guy. I'm just going to save this and clean it up. All right, so I hope you enjoyed that. And that is solving a geometry problem in section properties. And I'm so happy we got that solved now. It's just going to make this tool just even more awesome. Cheers.